behavioral modeling is about. In behavioral modeling, there could be some assignments, okay, which may be and the always else statements, or else some loop statements, or else some conditional statements will be used. So first let me go into the structural modeling, wherein we'll be using the data flow modeling in the middle, that I will debrief at that time. Okay, in structural flow modeling, detailed design functions are used, okay, such as your inverters, mux, adder, decoder, basic logic gates. These are used directly. It is connecting and rearranging different parts of the circuits. Okay, whenever we are connecting means some wire connections will be assigned, okay, to implement the functions that we are looking for. Okay, so for example, in the implementation of an half adder using the structural flow modeling, so the gates that we are using is called as your XOR operation is used and AND operation is used. So the inputs are your input 1A and your input 2 is your B. Your input is already assigned as your A and B, and the output is called as your sum and carry. Your input 1 is A and input 2 is B, and the output is called as your sum. And here also, if for your AND operation, your input 1 is your A and input 2 is your B, and output is called as your carry. And next one is called as your behavioral modeling. As of the behavioral modeling is about, okay, it is used to describe the behavior of the digital circuits based on the sensitivity parameter. Okay, so the designer describes the functionality by designing an algorithm in the form of a code. Okay, so the various boolean functions or expressions that is used is for AND operation will be using your ampersand symbol, and for your OR a straight line will be used, and for an invert a tilde symbol is used, and for the XOR operation that is called as your apostrophe is used, and for conditional question marks will be used, and etc. There are two subcategories as of this behavioral modeling is about. The first one is called as your continuous data flow, and next one is called as your procedural data flow. In the continuous data flow behavioral modeling, what we are going to do is we'll be assigning, for example, sum is equal to A, okay, up your B, and your carry is equal to A and your B, A and your B. Without this assign statement, if your output and input is defined and your sum is equal to your A and B, A up B, and as well as your carry is equal to your A and B is used, then that type of modeling is called as your data flow modeling. That type of modeling is called as your data flow modeling. And this continuous data flow modeling under your behavior modeling will be using assigning statements, okay, wherein the wire is the sum and carry. Wire is the sum and carry. What is the output that has been generated out of that particular logic gate is kept as wire here. Okay, in continuous assignment, okay, whenever there is a change in input will affect output immediately, because absence of controlling actions such as your sensitivity list. Since there is no sensitivity list, okay, so whatsoever the change in the input will be given to the output immediately. There won't be any controlling actions is available because sensitivity list is absent here. Here the output variables must be defined, okay, must be defined with an wire type, because they are continuously driven by digital logic defined on the RHS. And as of the procedural flow is about, here in this we are using assigning sum and carry. Whenever there is a change in the input, that will be reflected in the output, so only we need a wire symbol, okay, wire connection is to be listed because sensitivity list is absent here. But whereas as a procedural is about, okay, we have to use the always at. Our initial statement should be used. On the always at statement, we'll be using the sensitivity list as, say for example, the same example has been driven here. Input A and B, and the output is your sum and carry. And here the output will be saved, okay, will be saved and stored. There is only a register is used, register sum comma carry. Always at A means this is called as your, here A is called as your sensitivity list. Begin, your sum is your A plus B, and your carry is called as your A and B. So the RHS of the expression is computed continuously by its assignment to LHS happen only on the change in input A, because since the sensitivity list has been made with A, okay, whenever there's a change in the input A, your output gets changes. But whereas whenever there is a change in the output B, whenever there is a change in the output B, it may not change the output, okay, whenever there is a change in the input B, your output may not change instantaneously as your A changes. In this case, output variables must be defined as registers. whenever a continuous assignment, okay, as of this continuous and as well as procedural assignment is, in continuous assignment you won't be having, okay, you won't be having any sensitivity list, but whereas in procedural flow kind of sensitivity list is there. In continuous data flow modeling, that is your on continuous behavioral modeling, you will be using wire symbols, but whereas when we use some sensitivity list, we'll be using a statement called as your register will be used. Okay, and let me go into the fundamental assignments using the basic gates. First one is the design of basic gates. There are three basic gates we already know. One is called as your NOT gate, OR gate, and as well as your AND gate. So the first foremost statement is called as your header of the program, which is module. The operation is your NOT gate, A comma B. Your input is A and your output is your B, or else you can write as your input comma your out. You can write your input is A here and the output is your B here. Now we are going to use it as assign B is equal to tilt of your A. Here we are using behavioral without any sensitivity list. Okay, behavioral without any sensitivity list. So your assign B is equal to tilt of A in module. And next one is for your AND gate. So for the AND gate, the two inputs are your A and B, and your output is called as your Y. So your input is A comma B and your output is your Y. So here also we are using your continuous behavioral modeling. So your assign Y, that is equal to your A and B and your N module. And next one is called as your module OR gate. For an OR gate, your input is your A and B and output is called as your Y. Module OR gate, your input A comma B and your output is called as your Y. So assign Y, that is equal to your A backslash B, and this your N module. And next comes your universal gates. We know the universal gates and other gates. So the first universal gate that we are going to see is called as your NAND gate. So module NAND gate, your inputs are your I1 and I2 and output is called as your out. So module NAND gate of your I1 comma I2 comma your output, your input I1 and your input I2, and your output is equal to out. NAND gate of your, we are going to use here gate level modeling, that is called as your structural modeling. So NAND gate of your output comma your two inputs. Okay, as of your regular ordinary statement is about, okay, in the statements your inputs comma output could be there, but whereas as of gate level implementation, the first you should mention your output and then your inputs. Okay, module NAND gate, okay, and your NAND of your out comma input comma your input 2. So your output and your inputs I1 and I2. And next one is called as your XOR gate. As of your XOR gate is about, here also gate level modeling is used. So here we can see that input I1 and I2 and your module XOR gate of your I1 I2 and as this your output, but whereas your XOR of your output comma your I1 comma I2. And next one is called as your Xnor gate, and this comes under your other gates only. So as of Xnor gate is about, your inputs are your I1 and I2 and output is your out. So here also we can use your gate level modeling as input is your I1, input is your I2 and output is called as your out. Your Xnor of your out comma your input 1 comma your input 2. So whenever we are defining the header, in headers we have to define as your inputs first and the output second. In gate level modeling, whenever using gate names directly, output first and as well as your input assignment second. And the next one is called as your design of an half adder. Okay, the various combination circuits that we have studied after the logic implementation is called as your adders, subtractors, multiplexers and demultiplexers, encoders and decoders. So how to do this is, for a half adder we are having two inputs as your I1 comma your I2, and this is your sum. Okay, and your carry is called as your carry is this. Okay, so module half adder, you are not having any differentiation between assignments as of your headers about, either you can start with you can define your inputs first and then your outputs first, but and your outputs and next your inputs, but whereas there should not be a mess up of inputs and outputs. Okay, so module half adder, the outputs are your sum and carry and your inputs are your I1 I2. So the output is your sum and output is called as your Cout, and your input is called as your I1 and input is called as your I2. Now here also we are using the gate level modeling as your XOR operation of your, first is your output sum comma your I1 comma your I2, and next one is called as your AND operation of your Cout carry out input 1 comma your input 2 and N module. And how to define a full adder is, okay, in this full adder we have to have one thing in our mind. Whenever here the sum is the XOR operation of the previous XOR output and as well as the third input. So a half adder is defined as sum of two 1-bit numbers without carry. Sum of two 1-bit numbers without carry. But whereas as a full adder is about sum of two 1-bit numbers with the carry is called as your full adder. That is the definition of your full adder. So here what we can see is module full adder. Okay, the inputs are your I1, I2 and as well as your Cin, and outputs are your sum and as well as your C output. Okay, so you define your inputs and you define your outputs. So here see the input 1 and input 2 is given here, and the output is called as your, okay, and output is used by this next gate, right? So next XOR gate, right? So here we have to give a wire. Okay, this output should be carried to next one. So you give a wire as your S1. You give a wire as your S1, and your input I1 and as well as your input I2 is given to this AND gate, and the output is called as, and the output we can write it as your, this is called as, you let you take this as to your C1, and let this S1 is taken and this S1 is taken, and with the third input you are going to make an AND gate, and this is called as your, let you take it as your C2. So S1, C1 and C2. Okay, if we classify this only, we can go with the next operation. See here. So first wire is your S1, C1 and C2 we have done, and your XOR operation of your input XOR operation, this is your S1, so I1 and I2, and your AND gate, okay, and your AND gate is your N2, okay, which is called as your C1, I1 and I2. And for your XOR gate, next XOR gate is called as your input is, your output is called as your sum comma, your inputs are your sum is your S1 is an input and your Cin is another input. So that is called as your XOR operation. And your AND operation is, okay, and for this AND operation we are going to classify it as, so we can write this as to be your S1 is your input and your Cin is another output, okay, and this is the output is called as your C2. The output is called as your C2. So output is C2, your S1 is one input and your Cin is another output, okay, and your OR operation, as of OR operation is about, we can write it as your, here the C2 is one input and the C1 is another input and Cout is another output, okay, your OR operation of your Cout comma your C1 comma C2, like this. Whenever we are using multiple gates and the output is fed to another gate, means we have to use wire operations, okay, and here we have used the gate level modeling only. And this is another way of doing the full adder. Okay, in this full adder, instead of using the sum directly, S1 directly, here we are having three inputs. All the three inputs has been given with an AND gates, and the AND gates are given with an OR gate. A simple change in the assignment. Okay, and this is the design of two full adders with the design of an full adder with the two half adders. And here we will be using the statements of half adders directly. Here we can see that, so this is one half adder and this is another half adder. For this half adder, you will be having your input A and input B, and the outputs you can take as your, this is your S1 and this is called as your C1, S1 and C1. So half adder HA1 is equal to your S1, C1, input A and input B. Okay, input A and input B. And for this half adder, your inputs are your input is your this sum. Okay, this S1 is one input and this carry in is another input, okay, so that only given as your carry is in carry in is one input and this your S1 is output and your sum, and as well as this C2 is your output, C2 is your output. And finally R is used for taking the, okay, taking the addition of these two AND gates. So your R operation of this is your C1 and this is your C2, so your C out comma your C1 comma C2 and end module. And this is an half subtractor. When we go with the half subtractor, we can write as the two inputs are your I0 and I1 and the difference and as well as the borrow. As of difference, about the same XOR operation is done, but whereas whenever we give an input to a gate and that output is used for the other gate, means we have to use an wire assignment. So your input I0 has been inverted, so your input I0 has been inverted, the output that is got is your called as your X. So your wire of your x, not of your x comma your I naught, and your XOR operation is, and your XOR operation of your difference comma your I naught comma I1, and your borrow is equal to and of, and your borrow to find borrow and of your borrow comma your, okay, your x1, x1, and as well as your I1, okay, and this is your n module, okay. So and next one is your design of full subtractor, and for this full subtractor also, with the help of the diagram as like in your previous full adder, we can go out with this by using your XOR operation and as well as the AND operation. But only one thing is, here the wire assignments will be more, because here you used to invert few inputs, okay, and as well as we'll be taking that inputs to the next side. And next one is called as your design of a multiplexer. Multiplexer means, see, it will be having n number of selection lines, 2 to the power of your n number of your input lines, and only one output line, okay. As of your multiplexer is about, it will be having n number of selection lines, okay, 2 to the power of your n number of input lines, and as well as your one output line. Whenever we are having more inputs, okay, then we have to use this array classification. See, you are here, we are going to use it as S1 is to 0, means it is having two selection lines. One is called as your 0 and as well as your 1. And as of your input is about, it is having 4 inputs. One is called as your D0, D1, D2, and D3. And output is called as your Q. Output is called as your Q. So here we could write it as, and the wire symbols has been given as your Q1, Q2, Q3, Q4, M and N. Okay. So and again here wires, whenever your input is assigned as an array, that should be given as your wires. Okay, that is a mandatory condition. Okay, and here we are using the gate level implementation to do the assignments and to get the outputs. And next one is called as your decoder. Okay, the encoder and decoder. For a decoder, 2 is your 2 inputs and as well as your 4 output. When we look into the diagram, so here also the module decoder, that's a 2 to 4 decoder. Your inputs are your I0 and I1, and outputs are your output 0, output 1, output 2, and output 3. So inputs are your I0 and I1, right, and output is given here. So register. So as of decoder is about, the output should be saved at some point. Okay, that one bit is to be saved. So we are always use, as of your behavioral assignment is used, we used to keep the outputs for some time. So it is kept in the registers. Whenever always at statement is used, register should be used. So you are always at of your conditional assignments, your I0 and I1. When there is a change in the input, your output, it should be reflected in the output. So only always at of your conditional assignments of your I0 and I1 is given. When the 2-bit input changes, case of your case statements are your I0 comma your I1. When the inputs are your 0 and 0, your output should be your 1 0 0. When 0 1 0 1 0 0, and it's your 1 0, your 0 0 1 0, and when your 1 1, your output is equal to 0 0 1. So if not, none of this happens, means that then that is an invalid output. Okay, so depending on the input changes, your output may vary from your 1 0 0 to 0 0 1. Okay, this is an decoder. Okay, and this is an encoder, and here also behavioral modeling is used. And as of your encoder is about, okay, so we'll be having 4 inputs, 4 is to 2 encoders there. Okay, so what we can do is, here also your inputs and outputs is given in the header, and it has been classified as your I0 to I3 as input, and your output is your output 0 and output 1. Here also we are using your always as statement. Here it is constrained with this inputs of your I0 to I3. So we are keeping that as to be in a register. Your outputs are your output 0 comma your output 1, always set. When the input changes from your 1 0 0 to 0 0 1, your outputs will be your 0 0 to 1 1. Okay, and next one is called as your multiplexer and demultiplexer. As a multiplexer and demultiplexer is about, okay, we need to have the selection lines. When the selection lines, okay, when the selection lines S0 and S1, n number of selection lines, 2 to the power of n number of input lines, and only one output line. So here we can take as your I0 to I3 and as well as your S0 S1, and this is your output. So inputs and outputs has been classified. Now what we are going to do is, we are going to just invert the S0 and S1. Okay, S0 and S1, that operation is your NOT operation, and your AND operations are here. The IC7411 is used, which is a 3 input AND gate. When your S0 and S1, okay, both are S0 bar, S1 bar, and your input. S0 bar okay, S1 bar and as well as your input 1, and your S1 S0 bar and as well as your input 2, and your S0 S1 and as well as your input 3. All the 4 would have been done with the help of your AND gate, and then finally that are brought to the OR gate. Okay, OR gate operation has been done, and this is your end module. And as of your demultiplexer is about, here also your input is only one input. Okay, n number of selection lines, 2 power of your n number of your output lines, only one input line. Here also what you do is, first this S0 and S1 has been taken to an inverter. Okay, taken to an inverter, and that wires has been given here. So not of your S0 is given as your S0 negated, and S1 is as your S1 negated. And now we can write it as, now we can give it as your input statement is given. So the input is given as, okay, 1 2 3 and 4, and that is given to the AND gate. So your output not output 1, output 2, and as well as your output 3 is given, and this is your end module. And as of till now we have seen about the various logic gates and as well as the combinational circuits. For the sequential circuits and as well as for the flip-flops latches, we may see in the next session. Thank you all.